Good evening, everyone. We will start in a minute or two once everyone joins. So let's start with the session now. Let me share my screen. Yeah, good evening and welcome to the 11th live session of Physico-Chemical Processes for Wastewater Treatment. And we have been discussing on various advanced oxidation treatment methods. And these advanced oxidation methods, they are used for degradation of uh, these organic compounds that are non-biodegradable, right? So we have discussed a few methods, and now let's discuss about sono sonolysis method, right? So sonolysis is nothing but you are using ultrasound as the energy source, right? And when you provide ultrasound as the energy source, uh, gas is also passed, and that, like on passing ultrasound, the gas forms, like the dissolved gas in water starts forming bubbles, right? So these bubbles are formed, and depending on the gas solubility and depending on the amount of energy that you provide, the bubble size varies, right? So uh, these bubbles are formed, and when you keep on giving energy, and as the bubble growth takes place, it becomes very, like, unstable, and after certain uh, size, it bursts. So this bubble which burst, uh, it generates a lot of radicals, right? And it, the bubble has core and hot spot. So this has very high temperature and pressure, which are responsible for the generation of you know uh, the radicals and high energy, which allows the degradation of the organic compounds, right? So this is an example of uh, PFAS, which is an emerging pollutant nowadays. So, which are fluorinated compounds. So, that is why fluorine ions will be formed. Otherwise, in general, it should be CO2 formation taking place at the last, right? Now, smaller the bubbles formed here, more will be the energy and more will be the pressure, because size of the bubble is small. So pressure inside the bubble will be obviously more, resulting into more uh, uh, degradation because of the cavitation, right? Now the ultrasound that you are generating can, like, you need to have some setups for that. So you will be generating ultrasound in situ. So these type of reactors where you have sort of continuous stirring, or some tubular reactor where the process stream passes. So these are, like, uh, around a tube you have transducers which generate ultrasound, and ultrasound, it passes through this tube, right? And tube contains this process stream which degrades. And again, in this third tank you have process uh, water or wastewater, and on generating ultrasound through this various transducers, you allow continuous agitation so that mixing happens, and whatever the ultrasound generated through this transducer, it forms the hydroxyl radical and other radicals, and also you know it causes the degradation, and finally you will have the outlet purified or treated water. Next is, you can again combine ultrasound with any of the method. You can have uh, sono photochemical process, photo catalytic process, sono electrochemical process, right? So depending on the combination, you can have uh, the process name, and you can choose the process depending on your application, right? For example, if you combine sonolysis and electrochemical process, then what you are doing, you are combining ultrasound and electrochemical methods. So you will have electrodes and you will have ultrasound passed through that electrochemical cell, right? So whenever that happens, let's say you have these two electrodes, and when you pass uh, ultrasound like this here, so what happens, since ultrasound has good amount of energy, it not only enhances the mass transfer because of the bubbles formed, right? So bubble bursting with it will enhance mass transfer and reaction rates, and also it will increase the self cleaning of electrode. It will ensure that electrodes are clean, and um, the deposition of some byproducts it will also reduce, right? So that is the advantage of combining ultrasound with or sonication or sonolysis process with electrochemical process. Again, you can have um, sono UV or sono photocatalysis, where you are providing, uh, like for example, if you want to have UV, then in a closed chamber, this is the UV source, and you will provide ultrasound to the water tank, right? So you ultrasound is provided to the water solution, and UV is again passed, so that the process efficiency enhances. Again, you can have photocatalysis, um, where photocatalysts like TiO2 or some other photocatalyst can be used, so that you can have uh, better efficiency. Next process that is used in any industry is disinfection. So, do you have till this? Do you have any doubts till this point? Uh,
No, ma'am.
okay. Uh, just give me a minute. Okay, so now we will move forward with our next treatment method used in any industry, may it be sewage treatment plant or industry. That is, you provide disinfection to the wastewater stream, and disinfection would be the last step provided to any, like it usually is the last step in the treatment entire process, right? So what is disinfection? So disinfection is nothing but you try to inactivate or destroy microorganisms, and these microorganisms could be bacteria, viruses, protozoa, etc. And like, what does these terminology mean? Inactive means they are not able to reproduce further, or they are not able to multiply further. Not able to multiply further, which means that they will not be able to multiply, and now it will not cause increase in the number of microorganisms. And destroy means you kill the microorganisms, right? So by either of the way, you will be able to have a clean water, right? So now disinfection is more applied uh, for the cases of drinking water application, and here it means that whatever the bacteria, viruses, and proto or other microorganisms that are harmful to us, right? So they are, you know, targeted. Otherwise, there is sterilization provided where all the organisms they are targeted to be killed. Now, by which means you provide disinfection? So, if you have seen water treatment units in our home, uh, then you would have heard of UV, right? So, UV unit will be there in all the water filtration units at our home. So, that UV, it kills or it damages the microbes. Again, you would have heard that whatever the municipal water comes, right? So, whatever the water is distributed by municipality, it contains chlorine. So, what is the role of chlorine? Uh, it is used for disinfection, right? And disinfection itself means like even for floor, if you want to kill the microbes, so that phenyl is also also a disinfectant, right? But it is surface cleaning. And what you use for water is you can use either free chlorine, either combined chlorine, ozone, chlorine oxides, UV, etc. Right? Or there are some nowadays you can have a look into, for example, even if you boil water, it like in earlier days the most common method was to boil the water, right? So that you can have potable water at the end. While nowadays again there are nanoparticles or there are some specific materials used that has some disinfection property because of the drawbacks of each of these methods, right? So nowadays let's start with chlorine. And as you would have heard that in swimming pools, in the water that come from municipality, chlorine is the most widely used method for disinfection because of its easy availability, ease of operation, and also low cost, right? And it can be used in the form of Cl2, which is chlorine gas. Then this is chloride, right? So this hypochlorite is nothing but bleach, right? Then you can have CaOCl2 or CaOCl2. Like these has different valencies. Now, what happens here is Cl2 when it goes into water, it forms HOCl plus H plus and Cl, and this H plus HOCl it further dissociates into H plus and OCl minus. Now, basically, this is the compound which uh, you know is responsible for uh, the water disinfection. And if you see, because chlorine is a gas, so its solubility and its the species in which it, like the speciation or the form in which it is present in water, it depends on the conditions like temperature, pH, right? So if you look into the pH of water, then chlorine is usually present at very low pH in Cl2 form, while HOCl and ClO minus starts forming as you increase the pH. And six around 6 to 9.5, both HOCl and ClO minus they are present simultaneously. And at a point you will have a sudden increase in ClO minus, which could be the optimum point where you can use, right? So this is the equilibrium uh, between HOCl and ClO minus. Now again, if you look into water, then there are nitrogen containing compounds. Now if you specifically talk about wastewater, then it will have ammonia, it will have nitrates, it will have nitrite, and it will have some organic amino acids and so on. So these chlorine has the tendency, or hypochlorite has the tendency to combine with the ammonia or the organic amino acids to form some products like monochloroamine, dichloramine, trichloramine, or organochloramines, right? So these are some products which are combined chlorine, right? So these are all combined chlorine or organochloramines, and again these also can be used, but you should have some optimization. And you see, if you just want to have, you know, free chlorine as your uh, you know like you just want to have, because the efficiency differs, the dissociation differs, right? So what you can have is, from this curve you can see, depending on the ratio of Cl2 and the uh, ammonia present, then you can like there is a trend followed, and after some point only free chlorine will be available. So you can choose that region where you can operate for uh, disinfection. Next is chlorine dioxides. So chlorine dioxides, they generate free radical, and we have been discussing about free radicals in advanced oxidation process as well, that it is very reactive. But chlorine dioxide forms stable radicals, but it has very good reactivity, and it readily and violently reacts with reducing agents, because it's an oxidizing, because of its high oxidation potential. So what like due to its strong reactive nature, it is usually formed in situ or on site from chlorine and sodium chloride or some different materials. So by these reactions, right, so you can use chlorine or hypochlorite to form ClO2, and that will in turn form be responsible for disinfection. Now in various type of disinfectant, uh, if you want to compare, you need to compare their oxidizing power, and also if it depends on the amount of chlorine which is available for disinfection, right? So in the entire compound, what is the amount of chlorine that is actually available? So how can you find out that? So it can be find out using this formula, where available chlorine is nothing but the equivalent weight of Cl2 in compound per unit equivalent weight of compound. And equivalent weight can be find out using this formula, which is nothing but molecular weight per unit number of electrons exchanged. Okay. Yeah, so this is a question on that, on the same. What is the amount in percentage of chlorine available in CaOCl twice? So let's solve this question. So first you need to write the balance equation, right? So this would be the equation for chlorine. If you talk about CaOCl twice, then it will give you 2Cl minus CaO and H2, right? So to balance the equation, this would be the case. So this happens in the presence of H plus. So this redox reaction can be balanced by addition of 4 electrons on the left hand side. So how will you find out the equivalent weight? So equivalent weight of chlorine will be molecular weight divided by number of electrons exchange, which is 35.45 right, into 2 because it's in the form of Cl2, divided by the number of electrons, which will be 2, right? So it will be nothing but 35.45. And for CaOCl2, molecular weight is Ca has 40, oxygen is 16, 2 into 35.45, right? So which will come out to be 143 divided by number of electrons exchanged is 4, which means it is 35.75 as mentioned here. So if you take the ratio of these, this chlorine to compound equivalent weight, so and when you multiply you will get the percentage. So it's 99% chlorine is readily available for disinfection. So you can say that it has good oxidizing power, right? Is it clear so far?
Yes, ma'am.
So next is the use of ozone for the disinfection. Now, ozone is usually having pungent smell and it's very unstable gas. So, like, depending on the equilibrium constant, and this is the reaction. So, um, only certain amount of O2 is actually naturally present, right? So, O2 you need, O3 you need to generate in situ because of its unstable nature. So, this is the discharge electrode, right? Which uh, you know these are the electrodes, and when you pass oxygen from here, it allows the oxygen, a few of the oxygen to dissociate, right? And since it is dissociated, like the nascent oxygen, it combines readily with the oxygen molecule to form ozone, right? So this is the generator for ozone, and it is usually used like similar to sonolysis. This ozone is also generated very like near to your water disinfection unit, but it's very less common as compared to chlorine if you see. And next is UV irradiation. Now UV is nothing but, if you look into the wavelength, then below 400 or 300, like below the visible range, UV is the like the wavelength corresponding is for the UV, right? And UV, this UV, if you see, it has very high energy because of the shorter wavelengths, right? So this high energy, it has the ability to damage the uh, molecule, uh, sorry, not molecule, the DNA also of the microbes, right? And one of the major disadvantage of UV is its cost, because UV generation of UV, it requires high amount of energy, and which makes the process a bit costly, right, as compared to the other ones. And again, if you see, UV has various other harmful impacts on like us also. And this would, you would have heard that it can cause tanning, it can cause skin aging, and it, even if you further reduce the uh, wavelength of UV, then it can cause skin cancer or sunburn, and at the end it can have DNA damage as well, on further increasing the UV intensity or the energy. Now the amount of disinfection, it depends on the amount UV irradiation, right? Yeah, so for UV, it has to be dependent for a particular wavelength, right? So for a particular wavelength, which is denoted by lambda, what is the amount of intensity of UV light irradiated on the sample or on water, right? So that the disinfection happens. So the disinfection happens depending on the time of UV contact and the intensity of UV light. Now, over the other disinfection methods, chlorine has the tendency to form some byproducts. For example, hypochlorite can be left residual at the end, but UV does not form any byproduct as such, right? So, in that manner, UV is more advantageous, but obviously, it has very high cost as compared to the other ones. If you move forward, next is, what is the mechanism of disinfection? So, just a moment. Yeah. So, depending on the, uh, the disinfection method using chlorine or chlorine dioxide or ozone or UV, the uh, way it disinfects or way it inactivates or damages the microbes, it is different. For example, chlorine, it penetrates into the cell and causes damage to its organ and the basic nucleic acid which is responsible for membrane cell. So it causes the disruption of cell. Next is the chlorine dioxide, it inactivates the virus, while if you talk about ozone and UV, it damages the DNA. And if you like, since DNA is damaged, you can say that the cell is no longer or the microbe is no longer alive, because it will not be able to replicate and its cell also has been destroyed. Now, kinetics, if you look into, so usually this disinfection follows first order or pseudo first order. And there are like, depending on various assumptions and various methods, like in the classes for chlorination and for UV models with different assumptions, they are derived. For example, if you use chlorine, then you will be using the concentration, right? While if you are talking about UV, then the concentration of UV will be in terms of the intensity of UV that you are irradiating, right? So depending on these terms, you will be deriving the final form. And for all the cases, usually the first order equation is like this: ln C by C naught, sorry, C naught by C equals to, yeah, so this is the first order form. And if you um, linearize, it will be in this ln form: C by C naught equals to exponential minus kt. And when you take log ln on both the sides, you will have some form for the first order equation, right? So this will give you the uh, final form on how, with respect to time, the concentration reduces for like how will be the concentration change for both chlorine as well as the organics, right? Next is and yeah, for if you talk about UV, then as I mentioned, you need to take care of concentration in terms of its intensity of UV, which is irregular. And if you talk about disinfection practices, then there are specific you know uh, regulatory uh, norms which are made, which needs to be followed while looking into or while using any process or while assigning any process. So first is it should be like the final water should be pathogen free, right? Next is the final product, final water, it should not have any byproducts, right? Because if you have any byproducts, so that you will be consuming, right? If you are talking about drinking water application, so that can have again, like since it is byproduct, it can be toxic or it cannot be toxic, but anyways byproduct should not be formed, so that has to be taken care of. And certain amount of residual disinfectant level should be maintained, so that you uh, if there is any uh, changes or if there is any plus and minus in the pathogen concentration in the feed water, it is able to take care of that. Yeah, let's move forward. uh, Now we will be talking, so this was all about various methods for uh, water treatment, and various methods which are used in any industries, may it be like actual process industry or sewage treatment plant. What could be various methods used for the treatment of water? Now we will be taking cases of various industries, right? So as we have mentioned that depending on the industry, depending on the wastewater characteristics, the methods which are used for the treatment, it varies, right? So more or less all the processes will be used, but there could be some changes, right, depending on the industry. So let's first take an example of sugar industry. So sugar industry is basically using sugar cane, right? Sugar cane as the source of sugar production. So sugar cane is used, and first job is to cut the sugar cane and take out the juice from it, because mainly juice has the sugar in it, while whatever the left behind is the bagasse, which will be wet solid, right? So you would have taken sugarcane juice outside in the market, so you would be knowing that whatever the solid residue remains is nothing but bagasse. So now this is juice. Now this juice is very dilute, right? Very dilute because it has very high concentration of water and comparatively low amount of sugar, and it needs to be pre-treated with lime, and which the process is known as sulfitation. So that happens at high temperature, right? uh, and lime is added to remove all sorts of impurities present, right? And next is it passes through uh, clarifier, so as to remove any other impurities if they are present. Now you have purified juice. At this point, until this point you were purifying the juice, right? So now you have purified juice, sugarcane juice. And basically, since this has more uh, more water in it, so what you can do is you need to remove water out of it, which means that you want to concentrate sugar, right? So by removing water, so how can you do? You can use multiple effect evaporators, right? And that will remove water, and you will have more and more concentrated sugar uh, at the end. So after multiple effect evaporators, you will have concentrated uh, sugar, right? And that needs to be bleached, because if in case it has some color, right, or it has some microbes, that will also be removed. And at the end, whatever you have, a concentrated sugar mother liquor, that is sent to crystallizer, which causes formation like by super saturation, because you are like in a crystallizer you are achieving uh, a very a concentration of sugar which will be very high as compared to its dissolution or its solubility, which will cause the precipitation of sugar crystals, right? Now again, this sugar crystals are in a liquid phase, which is sugar solution, obviously. So sugar crystals need to be centrifuged, and at the end you will have sugar, right? So this is the process. And if you talk about the wastewater generation from this plant, then mostly you see this processes will generate the water with these parameters. And what would be the basic composition of it? It will have some different pH, it will have some TDS or suspended solids because of the usage of some solid, right? Because you are using some uh, sugar cane which can generate, like the solids were present here in this section, right? So it will generate suspended particles or suspended solids. You will again have some TDS, which is because of the dissolved solids. While you are using uh, sulfitation, there you use lime also, so you will have some TDS. Oil and grease comes from maintenance, and when you have oiling of pipelines and oiling of joints and all. And you will have COD and BOD, like more of BOD you will have, COD will be less, like you can say more of biodegradable components will be there, right? So you will have BOD to COD ratio very high, more than 0.5 at least. And that means you can say the contribution of COD, like it's mostly because of biodegradable organics are present, which can be removed using aerobic processes. Right, so in terms of treatment processes, you will mainly have preliminary treatment for the removal of the coarse material. Then obviously for any sorts of um, other suspended materials, you will have coagulation, flocculation, and sedimentation, right? And main important treatment here will be biological process. It can be activated sludge process, it can be trickling bed filters, or it can be lagoons, which is nothing but to take care of the high amount of BOD present. And you actually do not require any tertiary treatment in to degrade organics, because majority of the organics are biodegradable in nature, right? So uh, these are the major treatment units present. And at the end what you will have is uh, this should be the parameters of the treated water, right? So this is the guideline as per CPCB norms, right? So do you have any questions so far? Else we will move to the assignment. Okay, just give me a moment. Let's discuss the start the assignment. So first question is, what is the approximate temperature of the hotspot zone inside the cavitation bubble during phonolysis? So sonolysis, as we mentioned, that it has very high temperature and pressure inside the bubble that causes high energy generation of
5,000 Kelvin.
yeah, correct. So because of very high temperature and pressure, which usually in the range of 5000 Kelvin, it will cause the radical formation. So A is the correct answer. Yeah. Next question is DSA stands for dash. DSA means these are nothing but dimensionally stable electrodes, and these electrodes are used like in any electrochemical process which has very high conductivity, and also they are corrosion resistance, right? So they have very high corrosion resistance also, which means like that means they are stable electrodes. Okay. Next question is sonochemical reactions are carried out at frequencies between dash. So it is carried out at 20 to 50 kilohertz frequency. Okay. Next is which among the following is not the commonly used disinfectant for drinking water. So if you look into the options, free chlorine is a disinfectant, ozone is also a disinfectant, UV again, because almost all the household water purification systems, they will have UV system, right? You can observe this sometimes, but alum is never used for disinfection. So alum is the answer here. Next is correct value of Planck's constant. So that you need to remember, which is 6.6 10 to the power minus 34 joule into second. So next question is a numerical which says uh, potable water is disinfected by 10 milligrams of HOCl and the final pH measured is 6. What percentage of HOCl is not dissociated? So let's look in solve this question. So HOCl dissociates through a reversible reaction into H plus and OCl minus, right? So this is the question, uh, equation, and the equilibrium constant like pKa value is given as 7.54. So you can say that equilibrium constant Ka will be 10 to the power minus 7.54, right? So this is similar to pH, right? So pH has minus log to the base 10 hydrogen ion concentration, right? So similarly pKa is the equilibrium constant, so 10 to the power minus value, right? So that will be equilibrium constant. Now equilibrium constant can be written as H plus concentration, OCl minus and HOCl, right? That should be 10 to the power minus 7.54, right? So solve this to have 2.88 10 to the power minus 8. Okay. Now again you have one more hint, which is the final measured pH at equilibrium is 6. So again I have written this formula here. So pH is 6, which means that the constant minus log to the base, then H plus concentration is 6. So from this you can derive the H plus concentration, right? So which will be H plus concentration is 10 to the power minus 6. So how is it 10 to the power minus 6? This minus goes here, and if you want to remove log, you need to take anti-log here, and here it will be 10 to the power minus 6, like whatever the number is, 10 raised to that number, right? So this is the H plus concentration. So if you put up that value, uh, you will have the ratio of it, like you will get the ratio of concentrations of OCl minus is to HOCl, right? So you will have this ratio. So that ratio is HOCl equals to 34.7 times the concentration of OCl minus, right? Now if you talk about the mass conservation for chlorine, then it is contributed by the amount of percentage because of HOCl and OCl, which will give you 100%, right? So since you want to have in terms of HOCl, uh, like you replace here HOCl by this, so you will have OCl minus percentage, and OCl minus is the dissociate percentage. So HOCl undissociated will be 100 minus 2.8 into 34.7, right? So HOCl is 34.7 times OCl minus. So that comes around 97.16, which means option number C. So are you able to solve this? Okay, so I assume that it's clear. Moving to the next question. Which among the following is the wavelength range for UVC light? So UV can further be divided into three categories depending on the wavelength and their, the energy or the destruction ability. So it is A, B, C. And for C, the wavelength range is 200 to 280 nanometers, right? Next question is chloramine's residue decline to a minimum value, and the break point when the molar Cl2 to NH3 ratio is about 2 is to 1. Okay, so at break point of Cl2 is to NH3 2 is to 1, you will have minimum chloramine residue, and after that only chlorine will be present. Next question is find out the amount of chlorine which is available in CaOCl twice. So I guess this numerical we have discussed just back here, right? So like I guess it's the same question. So I'm not going in detail into this. Okay, so answer is 99. Again, if you have doubt, you can stop me and ask. And yeah, the last question is in sugar manufacturing, during double sulfidation process, the juice is heated to dash temperature and treated with lime and SO2. So the answer is 75. So here the temperature maintained is 75 degrees centigrade. Yeah, so do you have any doubts further? Like that's it from my side. You can come up with your doubts if you have. Okay, so you can go through the class notes, go through the lectures. If you have any more doubts, you can come up. I will be around for some more time. You can look and just let me know if you have any.
Thank you, ma'am.
Thank you. the ones who have joined later, you can, like I have already discussed with the assignment. So further, if you have any doubt, you can do let me know. Okay, so if you don't have any more doubts, I guess I will end this class here today. Thank you everyone for joining. We will meet in the next class. Thank you everyone.